Welcome to the third video on logic, where we're going to be talking about predicates and quantifiers. Now, to get started, I want you to recall what a proposition was. A proposition was basically, it's a complete sentence that's either true or false. So things like, 2 plus 2 equals 7. That's a proposition. That's false. Something like, what time is it? That is not a proposition because it's a question. Now, one example that I did about something that was not a proposition was something like this. X is less than or equal to 3. That is not a proposition because who knows what X is, right? The truth or falseness of saying X is less than or equal to 3 depends on the value of X. So now we're going to get a new definition of something, and it's called a predicate. And a predicate is just a statement involving a variable. So let me erase what I have written up here. And we're going to use predicates to kind of expand our repertoire of what we can do with logic. So here are some predicates. Remember, a statement that involves a variable. X is less than or equal to 3. There's a variable there, X, so that's a predicate. Computer C is infected. So I have a variable C that I'm saying, a computer that I'm going to label with the variable C that is infected. I can also have predicates that involve more than one variable. Country X is on continent Y. So these are all examples of what are called predicates. Now, we typically denote predicates with what looks like function notation. So we can say, the predicate P of X, or the predicate Q of X and Y, where P and Q represent the statements and X and Y represent the possible values. So here's an example that also shows how we can do this with Python. So P of X is going to be the predicate X is less than or equal to 3. Now, once we have values that are subbed into the variables, then we can talk about whether the predicates are true or false, because that will give us propositions. So for example, P of 5 in this example would be the proposition 5 is less than or equal to 3. P of 2 would be the proposition 2 is less than or equal to 3. So just like you did with functions in college algebra, when you substitute a value into a predicate, anywhere there's an X, you write a 5 in this case or a 2 in this case. And that's all there is to it. Now, we know just from being able to look at these that 5 less than or equal to 3, that's a false proposition. And 2 less than or equal to 3, that's a true proposition, right? Because we get propositions when we assign values to the variables. Now, here's some Python script, some Python code that checks this example up above. So here we start with line 1. We're defining a function that's just called P of X. And all P of X is going to do is return the Boolean value of X less than or equal to 3. So there's the function defined. Now we're going to assign A to be P of 5. So now X has the value 5. We're going to run the function, and we're going to return whether X is less than or equal to 3. Well, X is currently 5, so this will test false, so the function will return false. We can do that with B. A is going to be saved as false because that's what the function is. So we'll do that with B, where B is P of 2. So now we're going to run the function where X equals 2, return 2 is less than or equal to 3, and we'll get a true, so B is saved as true. So short Python code that will just test out, that just illustrates how this example works. All right, moving on. We can have more than one variable for a given predicate. So here we're going to let Q of X and Y be the statement X minus Y is equal to 4. So we can use Python tutor, and this is going to be a little exercise for you to do. What would you put in here to fix this code? So remember, you can click on edit in Python tutor, and that will open it up in a new window, and you can try to fix that code to make it work. How would we do this by hand? Well, q of 6 comma 2 would be, let's not use an equal sign there. This would be the statement or the proposition 6 minus 2 equals 4. Well, that's true, right? Because 6 minus 2 does equal 4. Q of 1 comma 5 would be the statement 1 minus 5 equals 4. Well, that's going to be false because 1 minus 5 is negative 4. And so on and so forth. Okay, so it's a nice exercise for you to go in and fix that code to make it work. All right, so that is the introduction to predicates. So let's move on now to quantifiers. I said before that one way that you could test truth or falseness about a predicate is when you plug something in for it. Another way is if you quantify it. Okay, so consider these two statements. First of all, we have the statement for all integers x squared is greater than or equal to 0. Now think about that. That's saying no matter what integer value I plug in for x squared will be greater than or equal to 0. Well, that's going to be a true statement, right? Because no matter what x is, x can be anything, right? X can be anything it wants to be, and x squared will be greater than or equal to 0. Now look at this second one. Some student in the class has a birthday in July. So the difference in between the first bullet and the second one is I'm saying something is true for all integers, and the second one is saying something is going to be true for some student. Okay. Now this one, I don't know if this is true or false. I would guess that it's probably true, but I can't talk to you to find out. But I would guess if there's 28 people in here, chances are one of you was born in July. Okay. So look at this paragraph right here. Each of these statements considers a proposition over an entire population or set called the domain. So just like domains for functions in college algebra, domains for predicates is everything under consideration. And then it quantifies how many elements or people or whatever in this set satisfy the proposition. So there are two main types of quantifiers we use. In this class, the only two we're going to use, the universal quantifier and the existential quantifier. And it's exactly what it sounds like. The universal quantifier is going to say something is true for all possible elements of the domain. And the existential quantifier, well, the keyword there is exist. This is going to say something is true for some element of the domain. So let's focus on the universal quantifier first. So the universal quantifier, and the way that we're going to write that from here on out is with this very strange looking upside down A. This means for all, or for every, or for each. When it comes before a statement, we're saying that the statement is true for all values in the domain. So the example that we had before, where we're saying for all integers x squared is greater than or equal to 0. Well, that's saying for all x, where x is an integer, x squared is greater than or equal to 0. And we already said that that's a true statement. So here's another one. Okay. So we're saying for all x plus 1 is greater than x. And the question is this true for integers? So my domain is going to be the integers. That's my domain. And I'm saying, is the statement p of x true for all integers? That is x plus 1 greater than x for all integer values of x? Well, I'm going to leave this also as an exercise for you to try on Python Tutor. It'd be a very useful one to do. The code is all given for you in this case. One thing to note is we're only checking it for a couple integers. We're only checking it for integers that are in this list right here, because it would be literally impossible to have the code check all possible integers. So we're checking it on, 5 or 6 of them to see if it works. Okay. If we get at least one of them false, then the whole proposition is false because this is a for all statement. Okay. So go through that and check it out and then see what happens when you try that. Let's move on to the existential quantifier. We denote this with a backwards E, and that means there exists, or for some, or for at least one. All of these mean the same thing. When it comes to for statement, it means a statement is true for at least one value in the domain. So here's an example. Writing this out in English, we would say there is an integer, because that's our domain. There is an integer such that x squared is equal to 4. Well, this is a true statement because we can find one integer that it works for. In particular, the integer x equals 2. That makes that a true proposition. So again, there's some Python code to check that. It's checking it on that same list of 5 elements. And if at least one of them is true, if it's true for at least one of the things on this list, then the whole statement is true. Excuse me, then the whole existential quantified predicate, which is a proposition, is true. Okay, so now what we're going to do is look at some examples. And before we do that, I just want to briefly show you the notes. Again, I want to emphasize your workflow should be reading through the section of the book, looking through the notes, and then working the examples everywhere, and then the practice problems. So these notes just give you more examples and a little bit more explanation of what's in the book. So read through these with the examples. And as always, I have these embedded videos in the notes that just give you more examples to watch someone work out. So watch all these embedded videos. And now I want to do a couple practice problems. So I want to do this example right here. And again, these are drawn from the practice problem. So I'm not going to do every single problem here. I'm just going to do some of them. I'm going to do this for P of 3. Okay. So P of X is the predicate. I'm just going to rewrite it. X plus 2 is greater than 5. So that means P of 3 would be the predicate 3 plus 2 is greater than 5. Well, this is false because 3 plus 2 is equal to 5, which is not greater than 5. So that's false. Okay, so do that for the other two examples for P of 2 and P of 5. Just kind of check your understanding. Let's move on to one a little bit more substantial. Let's look at this one. So C of X with the statement X has a cat. Okay, so here is my predicate. X has a cat. D of X is going to be the predicate X has a dog. F of X is a statement X has a ferret. And we want to express each of the statements below using quantifiers and logical operators. And we're told the domain is going to be all students in your class. So now we're not worrying about truth or false. We just want to write these symbolically. Okay, so let's do A, and let's do C, and let's do D. Okay, so a student in your class has a dog, has a cat, a dog, and a ferret. Well, we're saying this is true for some student, maybe more than one, but for at least one. So this is saying that there exists an X, where X is a student in the class. There exists an X such that they have a dog, they have a cat, so C of X, and they have a dog. There's our symbol for and they have a ferret. So let's put these in parentheses or brackets just to show that these all go together. But that's how you would write that symbolically. For C, I'm saying some student in your class has a dog, a cat, a cat, a ferret, but not a dog. So there exists a student in your class such that they have a cat, C of X, they have a ferret, F of X, they don't have a dog, so not D of X. Okay. Part D, no student in your class has a cat, a dog, and a ferret. So how do you say something like no student in your class? So nobody in your class satisfies these conditions. So one way to do it would say there does not exist a student in your class such that c of x and d of x and f of x. Now we're going to see in the next section, there's also a way to do this with a universal quantifier, but this way certainly works. All right. So moving on to the next part. Now we're going to be analyzing whether or not these are true statements or false statements. So let's do part A and part C and I guess part E. So part E says there exists an x just at O of x. Well, we should read what things mean first. So O of x is the predicate x is odd. L of x is the predicate x is less than 10. G of x is the predicate x is greater than 9. Okay, so this is what I recommend. Write these out in English, and then you can kind of analyze it a little bit better. So part A says there exists an integer x so that O of x. Well, O of x says x is odd. Well, I tell you what I'm going to do. I'm going to write all of them out in English first, and then we're going to come back and analyze them. The second one says part C says for all integers x, L of x implies not G of x. So L of x implies not G of x says if L of x, if x is less than 10, then not G of x. So how do you negate a less than? So not G of x would be x is not greater than 9. But this is the same thing as saying x is less than or equal to 9. So I'm going to write it like that. So going back, for all integers x, if x is less than 10, then x is less than or equal to 9. And again, we'll come back and analyze this in just a second. And then part E says for all integers x, L of x or G of x. X is less than 10 or x is greater than 9. Okay. So let's think about how you show these things are true or false. And I'm going to give you some guidelines down here. Guidelines. So the first one is to show a universal is true, demonstrate it's true in all cases. To show a universal is false, find one case where it's false. Maybe consistent and just say F. So keep this in mind when you're doing these problems. To show a universal statement is true, you have to demonstrate that it's true for every possible value in your domain. But to show that it's false, you only have to find one counterexample, one case where it's false. For existential, it's a little bit, it's kind of switched around. To show an existential is true, find one case, because one case is enough. One case where it's true. But to show it's false, to show an existential is false, you have to demonstrate it's false in all cases. Because remember, an existential is saying there exists something that satisfies this condition. Well, that's only going to fail to be true if it fails in every single case. So keep this in mind. Keep these guidelines in mind whenever you're doing these problems. Now, going back to these problems, let's look at part A again. There exists an integer. So if I want to show this is true, I just have to find one example where it's true. Well, there exists an integer that's odd. This is true, and just take x to be 1. 1 is an integer, 1 is odd. That satisfies the conditions, so there we go. Next, for all integers x, if x is less than 10, then x is less than or equal to 9. Well, remember, we're only dealing with integers. We don't worry about all those real numbers or those rational numbers in between 9 and 10. So yes, if something is less than 10, if an integer is less than 10, that's where your domain matters. If an integer is less than 10, then it is less than or equal to 9, so this is true. Then for all integers, x is either less than 10 or it's greater than 9. Well, think about your integers. Your integers look like this. Your integers are, 7, this keeps going on, 8, 9, 10, 11, this keeps going on. If something is less than 10, that means it's going to be everything, that's all the integers that are smaller than 10. If something is greater than 9, it's going to be going in this direction. All the integers greater than 9. All the integers get covered, right? 9 gets covered by being less than 10. 10 gets covered by being greater than 9. And then I have the arrows covering everything else. So this one is also true. So that's how you figure out whether or not these quantified predicates are true or false. You analyze them using these guidelines. Okay, that's all I wanted to say in this video. So if you have questions, as always, let me know.